Hello, this is the second physics video on the Carnot cycle. I am following Young and Freedman's University Physics, and I am in section 26. So the first part of this section, which I already did a video on, was on the Carnot heat cycle and refrigerator cycle, which is the kind of ideal heat cycle. It is done in such a way that all of the processes are reversible, and therefore it has the minimum possible amount of entropy loss, heat loss. So when it's expanding, it expands and heat is being added, it's isothermal. And when it continues to expand and no heat is being added, it's adiabatic. And then as the cycle returns, again, when there's a heat change undergoing, it's done isothermally, so it's reversible. And then when it has a temperature change, it's done adiabatically, so it's reversible. And so this is, as it were, the ideal heat cycle, because there is all the processes are reversible, and therefore there is the minimum amount of the highest possible efficiency. And so the next section that follows that Carnot engine and refrigerator material basically says that we're talking here about the second law of thermodynamics, that no engine can be more efficient than a Carnot engine, and no refrigerator can have a greater coefficient of performance or a greater efficiency than a Carnot refrigerator. And so all Carnot engines operating between the same two temperatures will have the same efficiency, the maximum possible efficiency, and this is regardless of the working substance. So Young and Freedman started us off by talking about ideal gases. But by the end of this section, we realize that it's not just ideal gases, but no matter what the working substance is, a Carnot cycle, a Carnot engine working between two temperatures, that's going to be the highest possible efficiency for any substance at all. And that is another way of stating the second law of thermodynamics. We have a number of ways of stating the second law of thermodynamics, or expressing the second law of thermodynamics in this chapter so far. And of course, we're going to go on in the next section to entropy and get a little bit more mathematical about the way we express it. Well, this particular section ends with an asterisk section, which means it's a little bit harder. I assume that's what that means. There are sections that are optional, shall we say, in the book. But this section, it's just one page, tells us about how the Kelvin scale is anchored in a way that it is not working substance specific. And the Carnot engine is the way that this anchoring of the Kelvin temperature scale without regard to substance is brought about. So you remember that for a Carnot engine, this relationship exists, that the amount of Q that's discarded divided by the amount of heat that's added in the front end of the cycle is going to equal the negative of the temperature at its cold point divided by the temperature at its hot point. Remember, this from the previous video is true of a Carnot engine. So all we need is an anchor point, and Lord Kelvin did this. Lord Kelvin lived in the early 20th century, and he suggested that let's go ahead and anchor this kind of a relationship by defining the triple point of water as 273.16 degrees. Now that may seem a little odd. Really? 0.16? I assume that's because Kelvin, I'm guessing a little bit here, but I'm guessing that Kelvin had projected where there would be zero kinetic energy in his mind, and he probably said, oh, 273 degrees, negative 273 degrees Celsius is probably what he concluded. And so he probably, I'm guessing a little bit here, feel free to correct me in the YouTube notes, that 273 degrees, I'm guessing he thought would be the triple point of water, and subsequent scientific experiment, etc., has shown that it's actually 273.16. And so kudos to Kelvin, even though it's not, he was a little bit off. And so basically we have this fixed point from which to anchor all the other temperatures in relation to the amount of heat. And so this provides a basis for the Kelvin scale that will give us the same results regardless of the working substance that we're dealing with. And so the Kelvin scale was anchored using the assumptions of the Carnot cycle. Well, this has been the rest of chapter 20, section 6 on the Carnot cycle.